Hey, Vest Scholars, welcome to this module. This lab, we're going to be looking at something called the water balance. If you look at the diagram in front of you, provided by NASA's Goddard Space Flight Center, you have a representation of the hydrologic cycle, one of the important biogeochemical cycles that takes um, that our planet thrives on, that life requires. I mean, other ones include the carbon cycle, the nitrogen cycle, phosphorus cycle. We can keep on going with that. You'll also note that when we think about looking for life on other planets, it's those same things we're looking for: water, carbon, hydrogen, nitrogen, phosphorus, sulfur, and so forth. The CHNOPS chemicals. So these are really critical, and of course, ultimately, these cycles are driven by plate tectonics. So they're driven by Earth processes, and they're driven by solar radiation. In the case of the water cycle, of course, both are involved, but solar radiation is the really big driver here. As you can see in this diagram, the sun is depicted over here. But one of our challenges here is it's one thing to describe this qualitatively and to say, yes, precipitation is coming into the area and other the water's going out in other forms or going back into the sky in other forms like evapotranspiration and so forth. It's a whole nother to try to put numbers on this and quantify it, which is what we try to do as scientists in when we're thinking about the climate, for instance, with the carbon cycle. We'll try to quantify that. And once we quantify it, we can begin to analyze what's going on in that system. And so it's really important for us to put together, when we can, systems diagrams that document the stocks and flows and potential feedbacks in a system. And that, of course, helps us understand what's going on. Systems in a if we model this, of course, as a closed system, models are always uh, not really entirely correct, or we might use the term wrong, as it was used by the person who coined the phrase, models are always wrong, but sometimes useful. Um, but regardless, we're trying to model a natural system so that we can understand how it works. And there's always going to be things that we need to add to that model to make it more accurate, but this is still very useful for understanding how these natural systems work. And so we're going to do that in this lab. We're going to model the water cycle using something called the water balance equation. And so how do we put numbers to these things? We're going to simplify this a little bit. Okay, so we got this diagram here. We're going to look at precipitation, specifically in the form of liquid water. We're going to look at runoff gathered from USGS streamflow data. Groundwaters, we're not going to spend much time looking at groundwater, but we will look at groundwater in the context of groundwater and surface lake water in terms of what we call the change in storage. We'll look at that in a moment, the part of the equation, and of course, evaporation and transpiration, which often are combined into a single term, evapotranspiration. So if we go over here to our original one of our data sets here, we're going to be comparing two watersheds. We're going to model these watersheds as though they are closed systems. And so what we would seek is a budget balance, a balanced budget. Water coming in balances with water going out over time. So over the long term, say maybe a year or two, or 70, water coming in should balance water going out. They should be roughly equal. So here's our water balance equation. In blue, precipitation, which is all the water coming in from other places, should equal the runoff in the watershed, which is taking water out. Evapotranspiration, also taking water out to go other places. And any change in storage. This is change in groundwater volumes and surface water volumes. So those combine together. Over the long term, there shouldn't, change in storage is often negligible. And so in a closed watershed system, and so we usually just look at runoff and evapotranspiration balanced with precipitation. What you're going to do in this lab is look at two watersheds. One is in Virginia. It's the North Fork of the Shenandoah watershed, centered around the USGS gauging station at Mount Jackson, Virginia. And you're going to contrast that, as is the case in your virtual field experience, with the San Juan River Basin watershed in the southwestern U.S., the Four Corners region, where we're going to be looking at water based out of using the reference of Bluff, Utah, and the USGS gauging station there. That watershed is quite a bit larger. As you can see here, this watershed The Mount Jackson watershed has a watershed area of 1,319 square kilometers, whereas the San Juan Basin watershed has an area of 96,015 kilometers. Regardless of the watershed size, it should be comparable. Another thing here is you'll notice that I've color coded the numbers here that we're going to be quantifying to go along with the equation here. So certain parts of this equation are related to the numbers that are up here. We are looking at precipitation for the year 2021 specifically, and then precipitation as an annual average. Same with runoff, same with evapotranspiration, and then we're going to look at change in storage. And the big question that we have in the lab is, well, the questions are these: how is the water balance different between the two sites? So, is one site have about? Does both sites balanced? Does one or the other or both have surpluses of water in terms of storage? We're looking at the change in storage, or does one have a deficit and one have a surplus? We're going to find out. What was the degree of that surplus? How do these numbers compare with what you might read about in the news with respect to the drought in those areas? And then what does the graphical anomaly between the long-term average and this last year tell us about what this last year has been like compared to what normal conditions are in each of the different respective watersheds? So how are we going to do this? Well, first of all, we need to find data. I've given you a data source. I've actually pulled in the data for the USGS gauging stations, and I've already normalized it for time. And so we're just looking at water volumes, and we'll do the calculation for that in a moment. Those values are going to automatically go in here. Once you do the calculations over here, all the numbers will show up because there's at the bottom of these columns there are calculated cells that are going to um, uh, calculate, and then they're going to populate these green cells over here for runoff. The blue ones, precipitation, you have to go to this data source. It's also the same data source you're going to go to for evapotranspiration, happens to be this one here for the San Juan. And you'll see there's two columns. There's the date, there's precipitation and evapotranspiration, both. And you can get those numbers at the bottom of these columns. And all you have to do is transfer those numbers into the spreadsheet here. In this gray, I'm sorry, this is the evapotranspiration here, and this is the precipitation here. You put those numbers in the gray boxes. Okay. Um, and then there's of course the precipitation annual and ET annual, which I've given you. I looked those up; those are kind of hard to find, so went ahead and gave you those values. So once you put the values you need in the gray boxes, and once you do the calculations in these gray boxes, you'll be able to then create a graph, and then you'll be done, right? So once you've done pulling in the precipitation and evapotranspiration numbers that go in these two gray boxes, you need to use this equation to deal with runoff. So how do we do that? You may or may not have ever actually put an equation in Excel, but we're going to start here in the second cell because we want to actually take into account, as you can see here, we want time 2 minus time 1 in our exploration here. And we want to multiply that by the quantity of uh, discharge at time 1 with discharge at time 2. This should be divided by 2. I'll fix that for uh, when it's yours. So, not divided by 22, divided by 2. Okay, so we want to get an average discharge and multiply it by the difference in time from between two moments in discharge. So these are moments that are off by essentially um, a day, because this is daily median runoff, versus for a 77-year period for in this case about Jackson, versus daily median runoff for the year 2021. So to put an equation in Excel, we always start with an equal sign because whatever the result of the equation is going to be equals is what's going to be in that cell. And I'm going to go ahead and put uh, two parentheses in here. And then, of course, I need to go over here to the time column, and I want to subtract this time minus this time, and I can close that parenthesis. And I know I want to multiply that by which is over here. Now I'm over here at the asterisk. I want to multiply that by um, the average discharge. So I'm going to put two parentheses in here again. I'm going to take this discharge. I'm going to add to it this discharge. I'm going to close that parenthesis. I'm going to divide by 2, close that parenthesis, close the final one, and hit enter, and there's my value. It's kind of a big number. When I do that, I can double click this bottom right-hand handle, or I can click and drag it on down. Either way, it works. And then now I have numbers in that column all the way down to the bottom of the column, where I also have now calculated values, as you can see. Okay. I'm going to do the same thing for column E, but now that I've done that, you can just rewind the video and see what I'm doing. But in this case, instead of using the discharge values over here, I'll use the same time values. I'm going to use these discharge values. So make sure you do that. Okay. Already calculated for you are the anomalies, because they're based off of columns B and D. So if I'm going to do this over here, I can go ahead and do this again. I'm going to go ahead and subtract the time, and I'm going to then multiply by the discharge here plus the discharge here. I want to put another plus in there. The average of those discharges, which gives me that value there. I go over here to this bottom right-hand handle, and I double click. And there I have it. Okay, so now that I've got the numbers in there, okay, and check and make sure the value is actually calculated all the way down, and you can see they did not. So I'm going to go ahead and drag on down here and make sure that they go all the way down, because there's actually a piece of missing data in here on this particular one. So this is one of these situations where you have to ask yourself, what's going on here? Why do I have a piece of missing data? And the reality here is that we're missing a piece of data, and I'm going to go ahead and fill it in. I'm going to put a number in here that should have been in here, which is going to be 1115, which will adjust things a little bit. I'm going to go ahead and double click or drag my data back on down so that I've make sure that I'm accurate. But this is it's an important skill, to be able to look at your data and make sure that make sure it makes sense, right? Because if it doesn't make sense, then there's something wrong. Um, all right, so I have not yet put my evapotranspiration or my precipitation data in. Again, that comes from this site. Once I do that, I'll have my final numbers for change in storage over here. And if things are all good for both the 77-year period and the last year, I'll have numbers that approach 0 in both cases and will be balanced. This cell over here has an if statement in here that's written out to, if it's not balanced, to tell you whether it's a deficit or a surplus. Okay. So that'll help you answer part of the questions. The other part is to go ahead and add some data to this chart. That's fairly easy to do. You're going to go to Edit Chart, and you want to add data that is going to reflect the median runoffs, the daily median runoffs, so column B, column D, and column F, and the anomaly. Because this is actually looking at this is the water volume in these columns. This is the runoff. And so let's just look at the runoff and the runoff anomaly. So to do that, we're going to add a series. And we're going to add a series here, the runoff, daily median runoff for the 77-year period. And you can see what it does. It's pretty interesting. This is what normally happens in the North Fork of the Shenandoah over the course of 77 years in terms of runoff every day of the year. And then if I add another series, let's look at specifically 2021. And you can see there is a couple of really big runoff rain events um, that these runoff events are associated with during those particular times of the year. But how do we compare? We can see that they're not too far off from each other this last year from the normal. So let's go ahead and add the anomaly, and you can see if there's no difference between the two, between last year and the big long average period, the anomaly should essentially be a flat line 0. And it's not. You can see there is an anomaly between runoff over the last year versus 77-year record, but not much of one. Okay, and so when you go to answer that question, you can use that information there to help you. Okay, and that's pretty much it, guys. That's how you do this, and then you'll have to do this all on your own for the San Juan data over here. That's not done for you either. You'll have to answer questions for both of them. You have the water cycle here as a reference in both cases. Well, you only have to answer questions for both spreadsheets. Let me correct that. So the questions refer to both. You're comparing the two sites. This is built off of also the virtual field experience that you've already watched, hopefully, as preparation for this lab, looking at these two sites in terms of a whole bunch of different stops. You've also seen examples of how human culture um, and human behavior is involved in those watersheds. So think of all of that when you're doing this lab, okay? And of course, all of this is going to feed into your APA paper for this module as well. All right, again, if you have any questions, check out our office hours, email me directly, or email your master teacher directly, and we're happy to help you. Have fun. Spreadsheets are awesome.